12, I'm just about to go through the work we did today on induction via divisibility. So here's example 1 from the work we did today, which was prove that 5 to the n minus 1 is divisible by 4. So this is going to require a different format from what we've done with the summation type, but we still follow the same procedures. So prove true for n equals 1. Well, 5 to the n, 5 to the 1 minus 1 equals 5 minus 1, which equals 4. And you're going to think, oh, I can just show that that's divided by 4, but what we're going to do, because we're going to do this later, is to show that that's 4 times 1, which means our answer is a multiple of 4, and hence is divisible by 4. So true for n equals 1, because we showed it in this format. Okay, step 2. Assume true for n equals k. And remember, this is for where k is a constant. Right? So here we go. 5 to the k minus 1. Well, what are we assuming? We're assuming that it equals 4 times, I don't know, some value, some integer value. Well, we'll call it 4m, where m is an integer. 1, 2, 3, 4, 5, any number. And I'm going to do another little step here. I'm going to go, well, add that one over. So 5 to the k equals 4m plus 1. And that's going to become important because what we're going to do is we're going to sub that in for 5 to the k. Okay, so step number 3, the meat of the sandwich. Prove true for n equals k plus 1. Well, what is 5 to the k plus 1? Well, 5 to the k plus 1 minus 1, well, that equals 5 to the k times 5 to the 1 minus my 1. But remember, I'm substituting in what's under the red line up there for 5 to the k. So I'm going to get, well, that's 4m plus 1 times 5 minus 1, which equals 4 times 5, 5 times 4m. I'm not going to write 20m because in a minute I'm going to factorise the 4 out. Plus 5 minus 1, which gives me 5 times 4m plus 4. So if I take the 4 out now, if I factorise the 4 out, then I'm left with 5m plus 1. Now, since m is an integer, 5m plus 1 will also be an integer. So since m is an integer, 5m plus 1 is also an integer. You don't really need to say that, but I'm doing it now so you can understand that that's what you've got. Hence, thus true for n equals k plus 1. And our fourth step, hence statement is true for all integers n greater than or equal to 1 by induction. So what have we got? We prove it's true for n equals 1, but we write it as whatever we're dividing by, in this case 4, by something. It might be 2, it might be 3. So 4 times or whatever you're dividing by something. We assume it's true for n equals k, and we rewrite the statement as 4 times m. You can choose another letter if you like, but everyone tends to use m, where m is an integer. Don't choose k. You've already got a k. Don't choose k. Rewrite it so that here your 5 to the k equals something, because you're going to substitute that back in. Then to prove it true for n equals k plus 1, you just take the statement and rewrite it, and then factor out whatever it is you're trying to prove it's divisible by, in this case 4. And because m is an integer, you'll get an integer 4 times some integer. So here we go. I'm going to do example number 2 now. So example 2, which is 3 to the 2n minus 1 is divisible by 8. Step number 1. Prove true for n equals 1. Well, 3 to the 2 times 1 minus 1 equals 3 squared minus 1 equals 9 minus 1 equals 8 times 1. True for n equals 1. Step 2. Assume true for n equals k. Well, 3 to the 2k minus 1 must equal 8 times m, where, now you need to write this, where m is an integer. You should say positive integer. 3 to the 2k equals 8m minus 1, plus 1. And that's going to be our crucial bit. We'll just underline it. That's what we're going to substitute back in a minute. Number 3. Prove true for n equals k plus 1. Well, we've got 3 to the 2 bracket k plus 1 minus 1. Well, that equals 3 to the 2k plus 2 minus 1, which equals, now you've got to know your indice laws, it's 3 to the 2k times 3 to the 2 minus 1. And here's where we make our substitution. I'm going to put in 8m plus 1 there. So I get 8m plus 1 times 3 to the 2 is 9 minus 1. I'm going to write that as 9 times 8m, because I'm going to factorise out the 8, plus 9 minus 1. That's the expansion of that brackets, which gives me 8 times 9m plus 8. Factorise out the 8, and I'll get 9m plus 1. And since m is an integer, 9m plus 1 is also an integer. So, true for n equals k plus 1. Step number 4, hence statement is true for all integers. No, it's a bit untidy. N greater than or equal to 1 by induction. Okay, the last one, example number 3. And we'll just have another look at that so you can see it again. What did I do? Proved it's true for n equals 1, wrote it as 8 times 1. Assume true for n equals k, put the m where m is some integer in, got 3 to the 2k, equals 8m plus 1. Proved it true for n equals k plus 1. Make sure you put the brackets around the k plus 1, so you get 2k plus 2. Expand, simplify, factorise, and you're there. So example number 3. What I've got to do, I've got to prove that x to the n minus 1 is divisible by x minus 1. Same steps. Prove true for n equals 1. X to the 1 minus 1 equals x minus 1, which equals bracket x minus 1 times 1. True for n equals 1. 2. Assume true for n equals k. Well, x to the k minus 1 equals n minus x minus 1 times m, where m is an integer. Still not finished with that line yet. because we need to go, well, x to the k equals x minus 1 m plus 1. Okay, step number 3. Prove true for n equals k plus 1. And by the way, that's what we're going to be substituting in. Therefore, x to the k plus 1 minus 1 equals x to the k times x to the 1 minus 1. Here's where we make our substitution, equals x minus 1 m plus 1, and all of that is times x to the 1 minus 1. So it's going to be some tricky expansion, not really. Inside these square brackets we're going to get mx minus m plus 1 x, we'll get minus 1. So that gives us mx squared minus mx plus x minus 1. Now, I want to get the m out. So I'm going to do this. Watch this. This is pretty tricky. Mx squared. I'm going to pull this x over here. Minus mx minus 1. Now look at this. If I take the x out of that and the minus 1 out of that, I'll get m as a factor, or m plus 1 as a factor. So if I take x out, I get m x plus 1. If I take minus 1 out, I get m x plus 1. And that gives me x minus 1 mx plus 1. So there's my x minus 1, which is what I'm trying to prove it's divisible by. And this here, since m is an integer, so is mx plus 1, because x is an integer. Thus, true for n equals k plus 1. My fourth step, hence statement is true for all integers n greater than or equal to 1 by induction. Okay, so that is induction via divisibility. Remember, you've got to put in m as an integer. Good luck.